Okay, welcome everyone to day 2 of Data Learning and Markets. My name is Jeff Shama with Industrial and Systems Engineering. I'm very pleased to start the day off. Our first speaker today is Nikhil Garg. He is an assistant professor of operations research and information engineering at Cornell Tech and part of the Jacobs Technion-Cornell Institute. His work is on algorithms, data science, mechanism design, to the study of democracy, markets, social systems at large. He received a PhD from Stanford University, and his industrial experience includes principal data scientist at PredictWise, which provides election analytics for political campaigns. Okay, see me after class, we'll talk about that. And Nikhil received the Inform's George Dantzig Dissertation Award and an honorable mention for the ACM SIGecom Dissertation Award. Welcome, Nikhil.
Great. It's really great to be here, sort of a lot of senior folks who I started my PhD doing a lot of reading of and sort of seeing works from. Yeah, so I sort of come from, I think, the same like applied probability, econ CS sort of background for a lot of folks in the audience, but I think I have the unenviable task of giving the most empirical talk at this workshop. So I thought I would start a little bit with sort of the methodological vision, which is what do folks like us, like what is the role of an applied probabilist in sort of to contribute to the understanding of systems, platforms, markets, what have you, sort of in this modern sort of age of ML. And the tentative answer that I'll sort of start exploring in today is that there's many challenges in the modern predictive paradigm. Both Eric and Nagin sort of mentioned a few of them yesterday, which we have censoring, missing data, distribution shifts, spatiotemporal heterogeneity, strategic behavior, all sorts of things. And these all have downstream consequences in systems that use or just make decisions based on data. And these sort of all also point to a need to understand the data generating process before sort of we do our empirical analyses or make our decisions. And so sort of the question then is can we write models that then inform empirical strategies to understand these sorts of systems more than sort of like a direct regression-based approach or whatever. So that's goal number one, is to maybe convince you that there's like a role for people like us to sort of do empirical social science in these sorts of systems. Maybe goal number two is to get y'all excited about an application I've been super excited about recently, which is government service allocation. So local government, society always likes to focus on federal and state government, but local government is super important, right? So like in New York, they manage about 8,000 miles of streets, 700,000 trees that line the streets, not including parks, and housing, sanitation, transportation. There's a whole bunch of things that that local government is providing and sort of maintaining. And there's a whole bunch of operational tasks that sort of need people like us to understand and improve upon. And so you have like learning problems. So what incidents are there? Like what problems are there out there in these systems that need to get fixed? You have the allocation problem of like out of the problems what things do you address today? What do you address tomorrow, and so on. And then you have an auditing understanding question of like in hindsight, did you do a good job of sort of making these decisions? And you can think about different objectives, but sort of at a high level, you might care about both efficiency, like did I handle the most urgent tasks in time, and then equity is sort of did I do that equally or equitably across different neighborhoods, socioeconomic groups. And I think what makes government service allocation different than a lot of service allocation in other systems is the first step is sort of in that first learning step, you actually have a huge crowdsourcing task, which many cities in the US and throughout the world, but it's a different number, use what are called 311 systems, which it's either a phone number or an app or a website or Twitter or a whole bunch of different avenues to actually make the complaint. But there's a way to complain to the local government about problems that need to be fixed. And this is actually the primary way that a lot of governments find out about what needs to get fixed, because they don't have active inspectors to go out and do the monitoring. And so, for example, New York system received about 2.7 million requests just last year. And these are all triaged by a central agency into the right agency, and then the right agency decides what to inspect and what to work on and so on. And this is just screenshots from the New York app that actually Ben took. He's in the audience, sort of a complaint he made about a damaged tree. Okay, so what's the pipeline of the system that we care to understand and optimize? So at some point, an incident is going to happen that needs to be addressed. So maybe a damaged tree, maybe a pothole, food poisoning, whatever. Some of the time, not always, and not immediately, that's going to generate a 311 report. So for example, just for numbers in the entire system, there's about 2.7 million complaints a year. In the Department of Parks and Recreation that we've been working with, it's about 70 to 100,000 complaints a year. Some of these, the agency is going to decide to inspect a subset of these. So for example, the Parks Department inspects about 2/3 of the report. And when I say inspect, I mean literally send out an inspector to find the tree that was complained about and then do a detailed inspection of what was wrong, right? So this is actually an expensive step. And then about half the time that they send out this inspector to do sort of a detailed report of what was wrong, it generates a work order. So then a maintenance crew comes in and fixes something. And in this entire pipeline decisions, you have a whole bunch of things that some of the speakers talked about yesterday, but that make both understanding and making these decisions a little challenging, right? So uncertainty, strategic behavior, distribution shifts, capacity constraints, all sorts of things. And sort of what my group and I have been trying to do is trying to understand and improve this entire system in collaboration with the Parks Department and a few other government agencies. Today, I'm going to spend most of the time talking about just this first stage, where the first stage is sort of an incident happens, when and how, how long does it take, if ever, for it to be reported, right? And this is based on a paper with my PhD student, Jia Liu. It was at EC this past year, and we're working on a journal version. And why do we care about this first stage? Because if there's already inefficiencies or inequities in sort of the reporting stage, then that's that's going to have downstream disparities in what work gets done, right? So a perpetual concern about these systems is that, for example, richer, more educated neighborhoods are just using the system more, right? They're complaining more conditional on receiving the same number of incidents. But the statistical challenge to understand this is how do we actually identify that people are complaining more, so distinguishing between, or complaining less, so distinguishing between underreporting and just maybe that was the ground truth, right? Maybe that neighborhood is truly facing fewer incidents. And by definition in these systems, the reason these systems exist is because we don't have external ground truth of what's wrong, what's wrong on the streets. Right? And so as a stupid example, you have two neighborhoods, one with 10 real incidents, another with 5 incidents, but one neighborhood just has 50% reporting rate. This is going to look identical from the agency perspective, right? The agency doesn't naively have a way to distinguish between these two cases. And this is a fundamental challenge in a bunch of contexts that a lot of empirical work has been sort of spilled on. So and it's called the benchmark problem. So in policing, you might care about understanding, is there inequitable policing in this neighborhood or sort of a sort of demographic of drivers? But how do you distinguish between sort of inequitable policing and inequitable sort of crime rates? In healthcare, you might care about under-testing, right? Is a population under-tested for a disease compared to what they should, compared to other populations? How do you distinguish between under-testing and sort of maybe that population just has better health and didn't need to be tested, and so on? And the classic way to attack this sort of benchmark problem is to try to use external data on ground truth, right? So have some other model, have some other data that tells you here's how many incidents I would expect to receive. So for example, I just read a paper in sort of trying to identify, over under policing of traffic incidents, and they sort of acquire data from sort of an external GPS like phone GPS data to try to calculate like sort of how much do different people or people in different areas actually end up speeding compared to sort of how much they get caught, right? So you can always try to, in this context, it would be go out and walk the streets and get a snapshot view of how many incidents there are in each neighborhood. Or you can try to construct a whole bunch of proxy measures like number of trees, their size, and so on, and then try to estimate ground truth. And what I just want to point out here is this approach doesn't tell you anything about delays. At best, it can tell you here's how many percentage of incidents were reported compared to should have been reported, but it doesn't tell you like it took a week to get reported as opposed to 3 weeks. And so the question that we try to answer in this paper is, can we measure underreporting without any notion of this external ground truth? For a variety of reasons, happy to talk offline, sort of external ground truth is actually super hard to get in our contest. It's prohibitively expensive. And the key idea that we're going to leverage comes from an old empirical Bayes idea, which is leverage the rate of duplicate reports about the same incident to identify the reporting rate, given that an incident has occurred. I'll give more details about this in a little bit. We do need to do additional work compared to the classic idea in our setting because we also have a time component, right? Incidents happen. They're like, like a tree falls down and then they get fixed, right? So they disappear. And sort of the original idea always thinks about like a static distribution that you want to estimate, like a sort of species don't go extinct in your measuring period. And so I'll go over the statistical method, sort of motivate, and you'll see, I think, why it's something I'm saying people with an applied probability background are like, would generate this method as opposed to other people. And then I'll tell you about what happens when we apply it to New York City data. Any thoughts or questions so far? Yeah, that's a good question. So what happens when you intervene on the system, sort of like things like that. We haven't looked at that at all. Sort of, there's been some other work about like, if you make it more visible that you're actually responding to reports, like, try to break people's cynicism that, nothing happens when you complain to the local government. There's been like some work that like breaking that cynicism helps a little bit. But we have nothing to say about that right now. Yeah, I mean, sort of, political science scholars sort of posit all sorts of reasons in all sorts of directions, right? So you could imagine that trust in government varies across neighborhood for historical reasons. You could imagine network access or sort of just like familiarity with the system sort of varies by neighborhood. I was talking to someone in the Indian government actually yesterday who she was saying that in India, sort of these systems are actually more used by the disadvantaged because as opposed to like the classic way of calling up a politician that sort of these systems are more tracked and more sort of externally audited, right?
For example, there might be some models that say richer people are less responsive than people that are poor. Then can I use some sort of like wealth data in order to?
Yeah, so today I'm going to tell you how to actually measure. So measuring that ends up being tricky because it's sort of entangled with the incident rate, right? How do you distinguish richer people just facing more incidents as opposed to reporting more? And so hopefully I'll convince you that there's a method to be able to distinguish those things. Okay, so what's the model? So let's have some type theta. You could think about this as super high dimensional, so encoding geography, incident characteristics, tree size, sociodemographics of the area of the incident, all sorts of things. An incident of type theta is going to occur according to sort of a semi-Markov process, sort of very little assumptions on what that process is. And so each incident I is going to occur at some time. Conditional on the incident occurring, there's a second process. Here I'm going to encode it as sort of enforce that it's Poisson. It doesn't have to be homogeneous, but it does have to be Poisson. And we're going to say that there's some other process with rate little lambda of theta at which they report conditional on the incident being alive. Right? So at some point the incident occurs, you don't observe when it occurs. hopefully at some point you're going to get a first report for that incident. You might get lucky. You might actually also get a second and third report or so on about that incident. At some point, it might also be inspected by the agency. And this is not, this is of course going to happen after the first report, but it's not necessarily going to happen after after the last report. And then at some point, and in the data we observe the inspection time because that's sort of in the data set. And at some point it's going to die. The incident is going to disappear. And you can think about it disappearing as maybe the agency fixed it, or maybe someone else fixed it, or maybe it washed away or whatever, right? And we're just going to model this as unobserved because it may be observed, it may not be, it may be observed if the agency was the one to fix it, but if someone else fixed it, it's not observed, right? So we're just going to assume it's not observed. Right, and then the research question, sort of translating the question I had earlier into the math of the model, is how does the reporting rate, how does the reporting process, little lambda theta, depend on the type? Right? And why does this matter? This directly tells you, the reporting process directly will tell you something about the delay. So how long did it take for the incident occurring to the first report happening? And this is in some sense a lower bound to how quickly incidents can be addressed. So right, if we assume an homogeneous Poisson process, this would just be on average 1 over lambda of theta. But you can sort of back this out for all sorts of processes. If there's a low enough reporting rate, maybe some incidents are never reported. And I just want to point out that it's not necessarily a bad thing that it varies by type, right? So, if more dangerous incidents, so a tree blocking a road or falling down on someone or about to hit a power line, you want that to be reported today, as soon as it happens, right? Whereas if it's a tree cracking the sidewalk or kind of overgrowing, or maybe a week from now it's going to be in the power line, maybe you're fine if the reporting rate is lower, right? So not all heterogeneity is bad, but some heterogeneity is bad, right? So if there's huge heterogeneity by the socioeconomic characteristics or just spatial spatial heterogeneity of different neighborhoods, then that's going to mean different levels of government service in different neighborhoods. And then, again, in the notation of the model, then the challenge becomes how do we distinguish big lambda of theta, which is the incident rate, and little lambda of theta, which is the reporting rate, right? And if you go back to the literature on a bunch of political scientists trying to do this, they for the most part, they ignore the problem. They just implicitly assume that incident rates are identical, that different neighborhoods are going to face incidents at the same rate, and then they just count the number of incidents that you observe that are reported in each neighborhood and declare any heterogeneity as being an incident heterogeneity. Some people do try to normalize, try to find external proxies for lambda of theta. But if theta is super high dimensional, right, so now it's by type, it's by neighborhood, by all sorts of things, getting a good proxy, actually getting, training an ML model that's accurate for every type ends up being a hard thing to do. And we tried doing it in our setting, and we just got completely different answers than what our approach gave us.
So how do you define the types? Just the neighborhood?
I'll detail what it is in the data, but incident characteristics, so size of the tree, how risky it actually was, what the reported, what the report type was. So did the report say it was a hazard? Did it say it was a root issue? All sorts of things. So there's incident characteristics. There's neighborhood, so an indicator for what census tract it was in. You could also put in socio-demographic characteristics of the neighborhood, things like that. Okay, and so what's the first insight once you write down a model like this is that duplicate reports about observed incidents tell us the reporting rate, right? Even though we never observe when it occurs to the time of the first report, if I knew this entire time period, right? If someone told me for every incident when it was born and when it died, then like all I have to do is to count the number of reports inside that interval that's drawn from a Poisson process, and then just do Poisson rate estimation, right? This is like a very standard homework problem if someone gives me the entire interval, right? The problem, and sort of this is the insight that the paper is just based on, that we can get some estimate of this estimated delay by looking at the number of reports inside of an interval, number of duplicate reports. Now we have to do a little bit more work because we don't actually know this this reporting period, and maybe worse is this reporting, and I'll show a plot in a little bit, is this reporting period varies a lot by incident, right? So like, it's going to be data dependent, that like a hazard thing gets reported today, the parks department's going to address it tonight because it's like about to kill someone. A root issue, they might get to it like a month from now, 2 months from now, right? So this reporting period varies a lot, and we need to be able to sort of handle that variation. So sort of which time am I going to be using?
Time between the accident occurs and the first report. Do you care about that?
No, so this is the estimate. This is what I actually care to estimate for my problem, right? But I never observed this, and so I want a method that gives me some hint at what this delay is, even though it's never observed. And the idea is that sort of if I get this entire, if it's an homogeneous Poisson, for example, if I know this interval, I get the rate by looking at the duplicate reports. By the assumption of the model, that tells us something about the delay. Now, you don't need to assume homogeneous, sort of you can do some other things to get around that. Okay, so then the task sort of boils down to, how do I find an interval under which I can declare the number of reports inside that interval as Poisson, right? Because if I had the entire interval, then this is a very easy Poisson rate estimation task that I can plug in whatever. But I need to convert it to a Poisson rate estimation task at first, right? And so maybe as intuition for what can go wrong, suppose, okay, for now, later I'll explain why this is the right choice, but for now, just let the beginning of my interval be the time of the first report, right? This is when I'm going to start counting the number of reports, but I'm not going to count the first report at that time. Now, suppose I just end the interval at some fixed time t later, right? So I'm going to look at starting at the time of the first report 30 days later. The problem is that incidents have very different durations that they're alive, right? So some incidents like get fixed like a day later after they first get reported. Some incidents get fixed 200 days later, right? And that's actually dependent on the type. More hazardous things get fixed earlier, right? And so you're going to heterogeneously bias your estimate downwards because you're going to be like counting times in your interval when the incident couldn't possibly have been reported, right? Because it was fixed. Who would report something that's no longer there? Okay, so what's attempt number 2? Attempt number 2 is, okay, so just look at the time of the last report. If it was reported at that time, then of course it wasn't fixed by then. Yeah. And so the theory carries through for non-homogeneous. The actual empirical sort of method that we end up doing we end up doing something that's slightly non-homogeneous, but not too much. But there it's like now you need, empirical tractability might require that assumption. But it's like surprisingly Poisson in the data that we looked at. Right? Okay, so maybe I don't have to explain it too much for this crowd, but like, why can't you just look at the time of the last report? It's because sort of you're systematically excluding time in which the incident was alive, but by definition you're encoding that there was no report in that time, right? So B is not a stopping time, and so you bias your estimates downwards if you end up using that. Okay, so what's the task? The task is we need to find some interval under which it's Poisson. And again, not a super hard theorem or anything. I think I think this is why people with like an applied probability background should do more empirical work. Is like, this is a very simple translational theorem, which is, what do you need? You need the interval to be, of course, after the incident happens and before it dies, right? You can't start counting like there should have been a report before it happened. And then you need both of these to be stopping times, right? And if both of these are stopping times, by which I mean, they're not dependent on the future events after those times, and that they're independent of theta, sort of given the histories up to then that's necessary and sufficient for the number of reports within that interval to be stopping time, to be Poisson. And then the last thing I'll say there is, this is not super surprising, right? That this follows from the memoryless property. But what was surprising is I couldn't find and please send me pointers if you know of these. I couldn't find a single paper in the literature that tried to empirically estimate Poisson rates where the observation interval for each row varied by sort of the process, right? And sort of that's exactly what's happening here, which is why sort of we need a result like this. But we couldn't actually find anyone, that seems like a lot of processes in real life. We couldn't find anything that actually tried to do that. Okay. So then, it should be obvious that sort of, the two attempts that we did earlier sort of each fail one of the conditions, right? Is if you do a fixed duration length, then it's going to be above the death time for a lot of incidents. If you use the time of the last report, that's not a stopping time. You're going to bias your estimates downwards. What we end up using is sort of, is because we have inspection times, right? We know when the Parks Department inspected it. Odds are they inspected it when the incident was still alive. And so sort of we can use the inspection time for the reports that were inspected. Okay, so then the method should be fairly sort of straightforward from here, is for each incident I, construct an interval within which reporting for that incident was Poisson. Then, pick your favorite Poisson rate estimation sort of empirical method and estimate the rates. Right, so for example, we ended up estimating what's called a zero inflated Poisson, which is sort of the slightest non-homogeneous thing you can encode, which is flip a coin after the first report. After that, there's going to be no reports if the coin comes heads. Otherwise, it's going to be Poisson. I mean. Yeah, so good question. So that is fine. So because it's sort of that's in the history.
Oh, I see. Because you're looking at the differences of the times within.
Yeah. So it's still going to be Poisson within that, and so that's totally fine. Yeah. I mean, it sort of okay. So there's a little bit is okay. So it's not going. It's of course by definition not going to be a function of the future, right? Because inspectors can't tell the future. Now, we do need an assumption that it's sort of independent on the theta that we actually use. It's sort of conditional on the theta that we actually use. It's not like looking at other information. Now, the inspectors do observe some things we don't, or that we do observe, but we haven't done the data analysis for. So like they observe the report text, right? So you could imagine that even conditional on like someone saying it was a hazard in the form, and the text is like all caps and says, please come fix this now, sort of thing. So yeah, that would bias our results a little bit. In some other work, we've like looked at the report text a little bit, and it doesn't seem to be so super predictive on top of the form-filled field. So like we think that bias is a little small.
What if the inspection or not is itself a function of the number of?
Yeah, so that's a great point. Is like, what if the inspection, like whether it's an inspection or not, is a function of this report? So something I'm going to sweep under the rug in a little bit is in this data set, the Parks Department only calculated the duplicates if it was inspected. So I don't observe if two reports are the same incident unless it was inspected. And so I can only do the analysis on the inspected set, which like totally is like that breaks the model. It's like potentially biases the results. We have some reason to believe it's like small biasing. We did some like checks. It's small biasing. But in another data set, sort of we replicated everything in Chicago, and there they sort of mark duplicates for everything. And in that case, sort of we get the same results, and it ends up being fine. But yeah, in theory, that totally sort of biases the results. Totally. So that would, yeah. So one, So we have to be careful about sort of like part of what you said is fine, part of what you said is not, right? So the part that's fine is if, again, maybe not an empirical estimation, but like if it's like non-homogeneous, so like you expect the first report to be immediate, but maybe the second report is like a slower rate or something. Yeah, so that in theory is totally fine. Now what's not fine is if the actual Poisson assumption is broken, right? So like if I'm the one involved in a fender bender and I've already called and someone told me that they're going to come fix it, I'm not going to call again, right? And so that actually breaks the Poisson assumption. So this method only works for public incidents, right? So only works for things like a traffic light went down or a tree fell down where you could imagine multiple independent reports. We do some sanity checking, like so the Parks Department gave us hashed sort of caller, email, phone number, names. And so we filter repeat callers for the same incident, ends up basically the same estimates. But yeah, totally, it's like some things are fine, some things are not. With another student, we're now working on sort of like a networked version of this. Is like, what if things aren't, like, it's not a public incident, right? It's like food poisoning, but you could imagine some sort of spatial correlation. How much can you like do the same thing without like full duplicates as opposed to spatial correlation? Okay, so then, okay, so this is in theory what I would do, right? In theory, I just set whatever Poisson process I want. I do the estimation. Now, like, I actually have to take it to data. I have super high dimensional types. So we end up doing Bayesian Poisson regressions. So sort of now, I don't estimate this for each type separately. I sort of say that as it depends on the type theta, depends on like, each of the features of the vector. So, maybe the coefficient on risk is super high, riskier things get reported more, but, and then I learned coefficients for like each census tract or each neighborhood or whatever. And then I have to do a few more tricks we have to do a few more tricks to sort of like make it empirically tractable. So for example, we do like spatial smoothing to like borrow information across neighboring census tracts, things like that. So we do the inspection time, like the data frame has like the agency telling us here's when we inspected it and here was the outcome of the inspection. So that's actually separate from the reports. That's just like the agency telling us. No. So you could imagine that this sort of my exact regression, sort of what's in my regression sort of could encode those assumptions, right? So I could have, for example, some coefficient for the risk. I can have another coefficient for the neighborhood. You could also ask me to like add interaction terms. But like all those type of assumptions are now just encoded in my regression. So we've started some work on sort of, you can imagine not just the number of reports, but you could imagine strategic reporting, like, I say that things are hazards so that inspectors come out quicker. We've just started that, but it's in the pipeline. Yeah, but I don't have anything to say about it yet. Okay, so let's see what happens when we apply it to the data. Sort of just quick stuff on the data. It's mostly public data. Those of you who haven't seen the New York City Open Data website, it's great. There's a lot of sort of just agency data just available online. The Parks Department did augment it for like some of like the repeat caller analysis, things like that we had to do. So we observe about 220,000 service requests over 3 years. And I mentioned this a little bit. So like some of the things we include in the type are like location, like census tract, reported characteristics, the inspector report, so on. And so some summary statistics this is just the plot I had earlier, is what is the time from the first report to the inspection, or capping it at 100 days. And so this is super heterogeneous, right? It's like most things are inspected within a few days, and then there's a long tail. Some things aren't inspected for like months. And then this is the question that Rod asked about, is this like conceivably Poisson? It's like, so what I have here is the x-axis is the number of reports in the observation period. The y-axis is on the log scale. And so if it was perfectly homogeneous Poisson, you would expect to see sort of this be linear. Approximately. I have some other plots for like homogeneous as opposed to non-homogeneous Poisson. There's some weirdness that there's like more just like one report than you would expect, which is why we ended up doing the zero inflation. But you know, I don't have to squint too much for being like this is approximately Poisson.
I guess my concern was we were very obsessed about the interval from first report to last
Yeah.
report, so that last report is not really like a stopping time. But if it's not really like Poisson, maybe these are just all good heuristics or not really happening.
Yeah, that's a good question. So like if I actually, so like certainly in simulation, if I use the last report, you can like make it arbitrarily bad, that estimation. I believe Je did run like what if you do incorrect estimation and then like what happens in practice.
A statistical test that we can run for
Yeah.
checking on
Yeah.
homogeneous Poisson process, not hypothesis or.
Yeah, so I have some plots in the appendix that I'll show you that like we didn't run a statistical test, but like some plots to suggest it's pretty homogeneous. Okay, so just a little bit on results. So maybe the first result is that it's like, at least if you just look at incident types, it's mostly efficient. That reporting rates are higher for more urgent incidents. So things that someone says is a hazard is reported at much higher reporting rates than things people say are not sort of not hazards. Same for like higher risk is like if the inspector says it was higher risk, it'll be reported at a higher rate than sort of if the inspector says it was low risk. So this is all like good news, and I'll contextualize these results in a little bit. Maybe the not so good news is reporting rates also vary substantially by neighborhood on this, even conditional on incident characteristics, on the same order as sort of as they vary by incident type. So this is a plot of sort of all of New York. So this is Manhattan, Queens, and so the difference in reporting rates can be on the order of like 3x between different census tracts. Yeah, so great question is like, so this is the raw reporting rate by census tract. You could also imagine sort of, okay, like now regressing this on like socioeconomic characteristics, population density, income, all sorts of things. Yeah, so certainly correlated with population density, but also correlated with other things, even if you sort of include population density and like income or race or ethnicity or things like that. Yeah, so this is rates, and so that's why you care about population density, not population. Yeah. Yeah, and so this is by space. You could also do it by socioeconomic, census characteristics. Ends up being similar. And just to contextualize this, like, not all of us speak in Poisson rates. So what does it mean for actual delays? So the implied average reporting delay for like a hazard, a tree in poor condition, high risk, our estimates imply about 2.5 days in Manhattan and about 4.7 days in Queens. Tree damage, moderate condition, not super high risk, 15 days and 28 days. A minor issue, 112 days and 209 days. And to answer your question, sort of, this is not with the interaction term. This is if I just have a separate term for risk or incident characteristics and a separate term for census tract. You could imagine this being different. You could imagine these two being closer together if I add an interaction term. Okay. Any thoughts or questions about this work? Yeah, so this plot doesn't do that at all. This plot is just the reporting rate per census tract. But now that I have the reporting rate, you could also now do a regression on like census characteristics. Or you could do another sort of, instead of adding coefficients per census tract, I could imagine adding coefficients for the census characteristics themselves. And then if I do either of those things, then you see that sort of these these are, of course correlated with population density, but also correlated with other things like race, ethnicity, socioeconomics, income, so on. No, so I mean, like, but then you sort of, then the question is, are there other reports? And yeah, so you're worried about the sort of the intervals being different, right? Because the Queen's government is less responsive or so on. But then you'd have to sort of argue that like they're different and the reporting sort of, like it would have to be they're different and the reporting rate is like non-homogeneous in a certain way for it to affect the result. Being different is not enough to bias the results. Yeah, which is why we needed sort of the theorem that like different reporting intervals are totally fine. Sure. Yeah, no, I'm not like sort of I don't want to sort of say, like I don't want to put too much emphasis on the socioeconomic, like there's certain spatial heterogeneity. Now, what's causing the spatial heterogeneity, that ends up being a tricky causal question that I don't really want to go. But if you just do the correlation, sort of yes, population density pops out, so do other things, even if you have population density in there. But yeah, totally get that I'm not sort of doing that in some super causal way, which is why I don't even have the results up here. Okay, so maybe I'll just spend like 2 minutes then, just because we've been doing questions throughout, in another sort of, as another example why I think sort of people with our sort of applied probability background can sort of help in empirical analyses. This is with Ben Laufer, who's right in the audience, and Emma Pearson, another professor at Cornell Tech. And this is sort of now how do we understand decision making, right? So far what I've told you is how do we understand reporting behavior. So an incident happens, a report's generated. Now I want to understand a report's generated, does the agency heterogeneously respond based on where the report is, right? And so now you have, each day the agency is solving a subset selection problem. Which incident, right, they're asking which incidents do I inspect or work on today, which incidents do I do tomorrow, and so on, right? So now it's a sequence of subset selection problems. And as researchers, we observe the inputs, right? So we observe report characteristics, and we observe outcomes, like which things did they end up inspecting and what were the outcomes of those inspections. And then we want to ask is, did the agency make the right decisions, right? Are they prioritizing the riskiest incidents, and did they distribute the risk fairly? And maybe just as another example is pointing out the naive approaches fail. So if you read the algorithmic fairness literature, what would they do? What they would do is they would look at sort of maybe the expected waiting time per neighborhood, right? So a report happens. How long did it have to wait in neighborhood A compared to neighborhood B in order to be inspected? Now, this is like clearly bad, right? So like maybe incidents in A are just riskier than incidents in B, like for the same reason why we needed a fancier model in sort of to do reporting. Okay, so maybe what if I just condition on estimated risk, right? What if I just do, now the algorithmic fairness person would say, okay, let's look at waiting time conditioned on neighborhood and the risk of the incident. Now, surely these need to be equalized. If they're not, that means there's some sort of disparities in response. But now, it turns out you can even explain this by capacity constraints, right? So if incidents in B are temporally correlated, right? So they all occur, a storm comes in, a bunch of trees fall down in a neighborhood, the agency has the capacity they can. Some of them are just going to have to wait. So it turns out the agency can be doing exactly the right thing, but these won't be equalized. So you end up needing sort of the same sort of type of sort of daily model in order to understand what decisions are they making versus what decisions can they make. Right, so we have to do some things about the uncertainty, about what data is missing and so on. But now what we can do is each day just look at the set that they made, the empirical subset selection answer they did. We can try to calculate the optimal subset that they could have done and then compare them in some way. We could also sort of try to fit a choice model. This is the approach that we're actually going with, is have a choice model with covariates, like which covariates, risk, neighborhood, and so on, influence the allocation, with ideally sort of the risk, the estimated risk, influence the allocation the most. Okay. So as the last slide, just maybe summarize the types of things that we're doing here. So today I talked about the first two, right? So a method to measure heterogeneous reporting rates, and then just briefly, a method to understand responses. You could also imagine doing the actual operational algorithmic questions. Okay, like, we've done the social science. How do you intervene optimally, right? So can you help them make optimal allocation decisions, or either through they're never going to actually implement here's the stuff you inspect today. They're never actually going to implement an algorithm that way. But you could imagine building a software tool that sort of is suggestive of here are the things that you should do, or here's how, in hindsight, what you did compared to sort of what an optimal thing might have done. And we're actively working on things like that. Cool. That's sort of all I had.
Thanks so much. Very nice work, Nikhil. Two questions. In the beginning, you mentioned 2 attempts, and they induce bias. That's clear. And you also made the point that people use similar approaches in the policy literature, so estimates are likely biased. Did you test how large that bias is versus the final estimates you get? How different the outcome is?
Yeah, that's a good question. I believe Zhao ran it. I do not know the empirical bias, how large it was. Clearly in simulation, it's very big, right? In simulation, those other methods sort of just track or at least what I do remember is empirically we did compared to just the number of incidents or number of reported incidents. There, it's completely uncorrelated with our estimates. There, it's sort of the estimates you get from that approach are completely sort of even slightly negatively correlated with ours, and it just tracks the number of trees in the neighborhood. Even if you normalize by number of trees, it's completely uncorrelated with our estimates.
Perfect.
Now, the actual Poisson ones, I don't remember the results of how different those answers were in our method compared to sort of the method I showed. But in simulation, the bias there can also be pretty bad.
Okay. And then the other thing is that you had this curve, the plot about the Poisson, and at the low end, it looked a little bit weird. That motivated you to have this correction for the low end. And I was thinking that there's actually some exogenous events like adverse weather events and whatnot, which could also be used as a starting point. As opposed to the first report time, you can use something like a windy day, an indicator for that, and just restrict attention to those. If you were to do something like that.
So we tried doing that as a latent variable. The issue is the number of variables now in the estimation is approximately the same as the number of rows, which gives sort of the model way too much freedom to sort of use that as a free parameter to try to back out the rate. Yeah, so we tried and didn't work.
Thank you.
Okay, I think we're at the end of time. A lot of questions generated by this talk, so let's thank Nikhil again.